Okay, in our last video, we looked at the periodic table and periodic trends, but today what I want to do is go into more detail about the electronic arrangement within atoms. And in particular, I wanted to bring up a little history. In 1913, a famous chemist named Niels Bohr and another chemist named Ernest Rutherford, although Niels Bohr tends to get most of the credit, proposed a really unique way of viewing atoms. And in particular, he proposed an idea where electrons are essentially orbiting a nucleus. So let's write this down. Where electrons orbit a nucleus and they orbit at discrete energy levels. Meaning the orbits are pretty well defined, meaning there's no halfway between orbits. You either have to be at one orbit or the other. All right, and this was called the Bohr model, and it held true for a number of years, about a decade or so, and it was supported by a fair amount of data. But what I wanted to do was to essentially show you what he was imagining here. So here's an image of what he was kind of proposing. So on the inside here, this black dot in the middle, that's our nucleus. So in our nucleus, we've got protons and we've got neutrons. And then outside of our nucleus, we've got these orbit levels, as he called them. And his idea was that electrons were orbiting around the nucleus almost like the moon orbits around our planet, right? And in this case, what we could do is we could have one of these electrons just orbiting around our nucleus and excite it with enough energy so that it actually hops up an energy level to a new and higher out orbit, right? So it's now going to be further away from the nucleus. However, when that happens, it's not very happy in that higher orbit, so it wants to go right back, which is exactly what they're showing with this arrow. And when it goes right back, it's essentially going to emit light or energy back out. So it was kind of an interesting idea. So one of the key takeaways from this is that there are discrete energy levels. This idea of discrete energy levels has actually held true for quite a while, although the idea of an orbit, like the moon orbiting around our planet, really isn't that true for electrons. Electrons are kind of funky, and so we'll talk about that later. All right, and this is pretty interesting. One of my favorite stories is how they knew that there were discrete energy levels and not that orbits could occur at any distance from a nucleus. Well, one of the interesting things that was discovered was helium. And so helium, we really didn't see much on Earth, but what this guy did was he took a look at a solar eclipse, and this was about 1868, around there. And when he looked at a solar eclipse and he diffracted the light coming off of that solar eclipse, he noticed this big yellow line. And so as you can see, there's kind of discrete spectral lines that seem to show up when we diffract this light. And each element has unique spectral lines, meaning that there's certain energy levels of light being emitted back out at us when these atoms are absorbing the radiation from our sun. So in this case, this energy of light could correspond to one of these spectral lines. But this is how we actually discovered helium, was from the sun, not helium on our planet. That wasn't discovered until a little bit later, but kind of an interesting side story there. All right, so this orbit idea was pretty unique, but like I said, it's not quite true. These electrons don't go around in a circular orbit like the planets do. So it wasn't until 1925 that another chemist came along. And this other chemist, his name was Erwin Schrodinger. And Erwin Schrodinger is kind of the pioneer of quantum mechanics. And essentially all he did was he refined this idea to a much better degree. So one of the things he reinforced was he said, yes, electrons exist at discrete energy levels. He called these quanta. And that's supported, again, by this idea of spectral lines, right? We see discrete levels of energy coming off of these atoms, which means that those electrons must themselves only reside at certain energy levels, all right? So that was one thing he confirmed. But one thing he kind of threw out the window is he said they are not in orbits. And what he found was that electrons are so tiny that they almost don't behave like a particle. When you get down to the really tiny level, like an electron, matter actually stops behaving like matter and starts behaving more like a wave, which is what he discovered electrons do. And because of that, we can't really know their exact position at any given time. So we can't know the exact position of electrons. And so what he started doing was a bunch of really high-level math showing that we can't know the exact position of an electron, but we know the probability of an electron being within a certain area. And so he started doing a bunch of advanced mathematics looking at probability maps, essentially. All right, so I did want to really emphasize this idea that Schrodinger came out and said they're not orbiting, but the word orbit you'll see a lot in terms of orbitals, and that's really just a throwback to Niels Bohr. So even though we're not talking about orbiting like planets, that root of orbit still shows up as a prefix in some of the other words that we use later on. All right, what I wanted to do was to break this down even further and start talking about electronic arrangement. And I know a lot of this seems kind of dry and tedious, but in our next video, we're going to talk about this in a lot more detail. So I just wanted to briefly introduce this. So the highest classification we have for electronic arrangement is called a shell. So the shell describes the location of a set of electrons. Of a set of electrons. All right? And when we write this out, it's oftentimes written out with an n number. So you might see n equals 1, or n equals 2, or n equals 3. These numbers right here indicate the shell that we're talking about. So are we talking about shell 1, shell 2, shell 3? But each of those shells can contain a unique set of electrons. And each of these shells has different energy too. So let's make a little note of that. So higher number shell equals higher energy in a pretty general context here. So if we're talking about shell 2, it's going to be higher energy than shell 1, for example. All right. So that's kind of the overarching idea of these discrete energy levels is we have these shells where sets of electrons can exist within them. However, we can actually break down these shells even further. So each shell, oops, let me rewrite this. So each shell is made up of subshells. And these subshells can be different types. Can be S, P, D, or F subshells. So Here we're talking about subshells. Up here we're just talking about the parent shell. And we said with the parent shell, we're looking at n levels. So is it n1, 2, 3, or so on. Where over here, we're talking about S, P, D, and F. So an example of this is if I'm referring to a 2s subshell, it's talking about an s orbital, atomic orbital, that resides within the 2 shell, meaning the second energy shell. All right, so it is a little bit confusing to think about. But I did want to kind of differentiate the shells and the subshells. The shell, in this case, is designated by the S. So this is going to be our shell, or sorry, subshell. Holy cow. Subshell, where the 2 represents the shell. All right, so let's go one step further. Each subshell is made up of atomic orbitals. Sometimes it's only one, but sometimes it's more. All right, and this gets kind of crazy when we start looking at these, but let's go ahead and start writing out some examples. So over here, we'll do an s atomic orbital. I'll just write s orbital. And an s orbital, if we look at it, is essentially just a sphere. So if we look at it, there's only one orbital that makes up an s orbital. So for example, we'd maybe just call this 1s or 2s to indicate which shell the s orbital resides in. All right, and then next, we can look at the p orbital. And with the p orbital, we want to actually pay attention to geometry because it exists in three-dimensional space. So let's imagine that we've got this little three-dimensional map right here. So over here, we've got our y-axis, we've got our x-axis, and our z-axis. The p orbital looks kind of like a dumbbell in space. So in this case, this would be a p sub y atomic orbital, meaning it's a p orbital that goes along the y-axis. So the y indicates the direction. All right. However, there's actually other types of p orbitals that also exist. So let's take a look at the other ones. And I'm not going to bother labeling all of these axes, but you can imagine we could have one that looks like this that goes along the x-axis. So rather than being along that y direction, it's going to be along that x direction right there. So we'd call that p sub x. That indicates the direction of that p orbital. And then last but not least, you can imagine we would have one where it's not in the x or the y direction, but rather the z direction. So let's go ahead and try to draw this the best we can. It's going to kind of be coming in and out, and this would be p sub z. So it's a little bit weird to think about each of these having a directionality to it, but we always have to think about this as being a three-dimensional probability map of electrons residing within this kind of dumbbell shape here. All right, so over here, we've got our s orbital on the far left, but then for atomic orbitals for p, because we have more than one of them, we would need to differentiate them as px, py, or pz. The reality is, though, they're all equal in energy. All right, now what I want to do is kind of take this one step further. And I'm not the best artist, so I'm going to cheat and pull up this picture from Wikipedia to show all of our different orbitals that we could run into in this orbital world. So up here, we've got our s orbital. And like I said, the s orbital is nice and simple. It's just a sphere. And then the p orbital we just did down here. And p orbitals, like I said, have directionality. It could be either px, pz, or py, depending on which angle or direction they're pointed in. All right, next, we've got our higher energy orbital, which is our d orbital. And as you can see, these look mostly like clovers with the exception of the center one that looks like almost a donut with a barbell going through it. These are pretty hard to draw, which is why I didn't even bother attempting them. But you can see, again, we've got this kind of directionality that's describing the specific orientation of that orbital. And then last but not least, we've got the hardest one to draw, which is the f orbital. And I like just showing pictures of these because they're more just mathematical representations of the probability map, right? So again, this has directionality too. All right, so I know it is a little bit confusing, but one important thing I wanted to leave you with is that you can only fit up to 2 electrons in any one of these particular orbitals. Up to 2 electrons in a given atomic orbital. Whoops. All right, so let's go ahead and look at the s orbital, right? So if we think about the s orbital, we've got one atomic orbital that makes up the s orbital. So in this case, it can fit 2 electrons in that orbital, right? But when we look at the p orbital, we have 1, 2, 3 sets, meaning we can fit 2 electrons into any of those. So if we add this all together, we can fit 6 electrons in our p orbitals. All right, and then after that, we've got our d orbital. We've got 5 of them. Each can fit 2 electrons. So all together, they can hold 10 electrons. And then last but not least, we've got our f orbital. We've got 1, 2, 3, 4, 5, 6, 7. Can fit 2 electrons in each, which means at full capacity, all of these f orbitals can fit 14 electrons. All right, so that's where we're going to stop now. In our next video, we're going to look at electronic arrangements in a lot more detail, but I just wanted to introduce a lot of this basic terminology and introduce the shapes before we jump into that.